Now let's look at the solutions to this rotator thingy in a little more detail. So to recap just the basics of the solution here, the energy levels go like h bar squared over twice I times the quantum number L times L plus 1. But that's basically like the quantum number L squared. And L can be any integer 0, 1, 2, 3, up to infinity. So the value of 0 energy is valid in a rotating solution because it doesn't have that pesky boundary condition of the particle in the box. Also, the angular momentum squared is equal to h bar squared times L plus 1, so it just doesn't have that 2i in a denominator. The z component of the angular momentum is equal to h bar times the quantum number m sub z, and m sub z can be any value between negative L and positive L. So that means that there's twice L plus 1 values of m sub z. Now the energy, remember, we can express as hc times wave number. That's our old E equals h nu Planck's law there. And so what we're going to do a lot in this class is actually use wave numbers effectively as a unit of energy. And as often as I can remember, I'm going to designate it as E sub little nu tilde, little wave number symbol. And this is equal to the energy in joules divided by Planck's constant times the speed of light. And overall, this energy in wave number is expressed in wave numbers. And the reason we do this, we're going to see, because it scales. We can remember values. So energy in these wave number units is h bar squared over now 2hci, that hc has found itself in there, times L plus 1. And that is equal to h bar, because one of the h bars is killed by the h in the denominator. So we have h bar, but there's a 2 pi left over, so h bar over 4 pi ci times the quantum number L times L plus 1. Now that's equal to, we can just take that whole leading expression and call that B. So the energy levels are equal to some value B times L plus 1. And this thing, the B value, is known to rotational spectroscopists the world over. So we just call it the B value. And the B value is actually equal to 16.86 AMU angstrom squared wave numbers divided by the moment of inertia, when the moment of inertia is given in the units AMU angstrom squared. You can derive that. That's what h bar over 4 pi ci is if the units of inertia are AMU angstrom squared. These are these things we call atomic units, and especially we've gotten in rotation, the typical value for the moment of inertia is going to be anywhere from 1 to some tens of AMU angstrom squared, because a 1 angstrom bond with a 1 AMU weight on the end of it, in other words a hydrogen atom, that's got an intrinsic moment of inertia of about 1 AMU angstrom squared. And as we start to put heavier weights out of slightly longer bonds, you get numbers that get into the tens of AMU angstrom squared. And that gives you the characteristic. I think it's really, really important that you know that what the molar weights of atoms are, and that there are a few, anywhere from 1 on up, right, from the periodic table, and also that you just know instinctively that that a bond length is an angstrom or a little bit longer. Those are things you really ought to know. And this means the B value goes from, let's say, 20 wave numbers down to about 1 wave number, and then for larger molecules it can get much, much less than 1 wave number as well. So now let's look at this degeneracy in a different way. I'm going to put the m sub z quantum number across the top here from -3 to +3, and I'm going to put the L quantum number, the principal quantum number for this rotational problem, going 0, 1, 2, 3, going upward, and we're going to draw little lines where we have states. So there's a state at 0, 0, and then there's 3 states with L equals 1. There's an L equal minus 1, L equals 0, MZ equals minus 1, MZ equals 0, MZ equals plus 1, all for L equal 1. We got 5 states when L is equal to 2, going from minus 2 to plus 2. And finally, we got 7 states when L is equal to 3. This should look really, 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 really familiar. And in fact, it is going to crop up again when we deal with atomic states, because one of the things the electron is doing in an atom is rotating around the nucleus, and the rotational component of that solution is very much what we're looking at right now. So we have 1, 3, 5, and 7 total states in these first 4 energy levels. So the energy levels are given by the principal quantum number, L there. The degeneracy is twice L plus 1. So there's 1 state in the first level, 3 states in the second level, 5 states in the third level, 7 states in the fourth level, which has quantum number of 3. So all told, there's 16 states sitting here for 4 distinct energy levels. Now we're going to look at some of these solutions in a little bit of detail here. So let's start with the Y00, the L equals 0, M sub z equals 0 case. This one's pretty easy. First, let's put a z-axis up here, because we're always interested in the z component of angular momentum. Well, that's 0. So I've got a little red dot there to designate that being 0. The momentum squared is 0. The angular momentum is 0. The z component of the angular momentum is 0. This one's pretty dull. There's no rotation, there's no nothing about that. But there still is a wave function. This is a valid solution. And in fact, the actual normalized wave function, y00 of theta and phi, is equal to just the square root of 1 over 4 pi. There are 4 pi steradians in a sphere. If you subtend a full solid angle of a sphere, you get 4 pi steradians. And so the normalization constant is just 1 over 4 pi. And if we draw 3 Cartesian directions here, this thing just looks like a blob. So in any direction, the value of the wave function is 1 over root 4 pi, and it's got nothing much to say for itself. So it's this completely featureless probability distribution of the orientation of the object. Think of this, remember, a model of a diatomic system. This is saying that in the ground state, where there's no rotational energy, there's also no sense that that little diatom, that little dumbbell, is oriented in any particular direction at all. It's just sort of blobbed out, and you can't really tell at all where it is, which is kind of weird, but that's what quantum mechanics does. So the other thing is that there's no zero crossings, since this is just a blob. So there's 0 nodes in the angle theta, and there's 0 cycles in the angle phi. So this is pretty much completely featureless.